Alright, so this is homework 4 for transport 1. We have a holding tank that has a pipe flowing vertically downward into a jacuzzi. And it goes all the way to the bottom. And then here we have another pipe that goes from the jacuzzi to a pump, and then this pump takes our water that's in our jacuzzi and that was in the holding tank back up and into the holding tank. The holding tank is 3 meters tall. The holding tank also has a diameter of 30 meters. And the length of the pipe that flows vertically downward from the holding tank to the jacuzzi is 7 meters, and it has a diameter of 1 meter, so this pipe's diameter is 1 meter. And this water flows through this part, which is a 10-inch diameter horizontal nozzle. The water depth in the jacuzzi is 1 meter. And because this length total is 10 meters and this right here is only 1 meter, we know that from here, which is the water level in the holding tank, to the height of the water in our jacuzzi, this is going to be 9 meters. This is our starting position, so position 1. And here where it exits the pipe that goes from the holding tank to the jacuzzi, this is position 2. What we want to know is how much power this pump requires. This 9 meter height difference is the height that the pump needs to pump water. So from here to here, that is 9 meters, and that is how far the pump needs to pump the water between the jacuzzi and back to the holding tank. So now what we're going to use is an energy balance equation in order to find the velocity at our point 2. So the pressure at 1 minus the pressure at 2 over our density of water, plus the acceleration due to gravity times the quantity of the height at 2 minus the height at 1, plus the velocity at 2 squared minus the velocity at 1 squared over 2, and that's going to be equal to 0 because we don't have any work due to flow and there's no frictional heating. So at point 1, our pressure is going to be 0 because this is open atmosphere, and P2 down here, that's going to be equal to the density times acceleration due to gravity times the height there. So what we're going to have is rho, g, and h, but our h is going to be equal to 1 over rho, and our densities cancel, and that'll be plus acceleration due to gravity, and that is going to be equal to z2 minus z1, which is -10, plus v2 squared, and our velocity at point 1 is going to be practically 0 because of how large this tank area is. So that'll be the velocity at 2 squared over 2 equal to 0. Solving that, we get -9 times acceleration due to gravity plus our velocity squared over 2 equal to 0, and that ends up being that our velocity at point 2 is equal to the square root of 18 times the acceleration due to gravity. If we were to do that up at this point, say that our water exited here, we would end up getting the same answer because here our pressure would be also open atmosphere, so it would be equal to 0. So this term would go to 0, but this change in height is -9 instead of -10. So then we would end up getting the square root of 18 times acceleration due to gravity. So while I was looking back at my problem, I realized I made a mistake. This should be P2 minus P1, where P1 is 0, and this is our rho GH, which ends up, it doesn't affect the problem because I kept this positive, which is what it should be, and it ends up getting negative 9G. So we can now find our flow rate, which is Q is equal to the area at 2 times the velocity of 2. Our area, we are given that the pipe has a diameter of 10 inches, so we need to convert that to meters. So 10 inches, 1 inch, 2.54 centimeters, and then 10 centimeters in 1 meter. So there's that, and that's the diameter, so we need to divide that whole thing by 2, square that, and multiply it by pi to get the area, and that will be multiplied by our velocity, which is the square root of 18 times the acceleration due to gravity. So looking back at this, I realized I made a mistake. There's 100 centimeters in 1 meter. So that is the flow at 2. And now what we need to do is use an energy balance for position 3 to position 4, which we're going to say is from the top of this surface of the water, and position 4 is going to be at the very top of this surface as well of liquid. So we know at this point our pressure is at atmosphere, so this is going to be equal to 0, and same here, our pressure is going to be equal to 0 because it's exposed to atmosphere. So when we go to do our energy balance, we're going to have P4 minus P3 over our change in density, but that's going to be equal to 0, plus the acceleration due to gravity times the height at position 4 minus the height at position 3. And then for our change in velocity, our pipe is the same diameter or radius throughout, and it has the same area. So we don't have a change in velocity from here to here. So we can just go ahead and not write that part. But we do have non-flow or work per unit mass. And when we go to solve that out, we are left with 9 times the acceleration due to gravity, which is equal to the non-flow or work per unit mass, because our change in height here from 4 to 3 is 9 meters. So we now have our work per unit of mass, and we have our flow rate for Q2. So we know that power is equal to the mass flow rate. So that's going to be Q2 times our density of water times the non-flow work per unit mass, which is equal to A2V2, our area times our volume times the density, and we're going to go ahead and put in 9 times the acceleration due to gravity. And our area is pi times 0.254 divided by 2 squared, and our velocity is the square root of 18g. So that is our mass flow rate, and multiply that by 9 times the acceleration due to gravity, and that gives us power. So we have our system here, and in order to have the amount of power that we calculate down here to be put into the system, we need for our pump to have energy supplied to it. So we said in class like that it was plugged in. So energy is being put into the system, or power is being put into the system. So in order for the temperature of our water to not change, and for it to stay at that constant temperature, we need to incorporate a chiller into our system to remove the power that was put into the system. So a chiller would be necessary.